Kia ora koutou. Hello, everybody. Thank you very much for tuning in. So when surveying and recording excavations over multiple field seasons on Ahuahu or Great Mercury Island, we face several issues regarding the precision and accuracy of our geospatial data and how these data are checked and managed. So in this presentation, we just want to briefly outline these issues, as well as why it is important to address them, how we have dealt with and continue to deal with them, and some of the lessons that we have learned along the way. First, a quick bit of context about Ahuahu. It is a privately owned island that lies off the eastern coast of the Coromandel Peninsula on the North Island of Aotearoa, New Zealand. And since 2012, it's been the focus of intensive archaeological investigation in a joint partnership between the University of Auckland and Auckland Museum, and in collaboration with Ngāti Hay of Wharekāhau and Sir Michael Fay. Research aims focus on Maori human-environmental relationships, gardening practices, chronology of occupation, raw material use, and settlement pattern. Now, as with most archaeological projects, we generate a range of geospatial data. Total stations are our primary tool for recording spatial data. These include three-dimensional locations of all artifacts over 2 centimeters in size, as well as the extent of deposits, features, and excavation units. We also record points across surfaces to create triangulated irregular networks, or TINs. We use GPS units for remote spatial data acquisition, survey and recording, digital cameras for photogrammetry of excavation units and features, as well as general photographic documentation, and laser scanners for generating 3D models of excavation units and also wider landscape features. And all geospatial data are integrated into a GIS and properly aligned. So fieldwork on the island can go on for weeks at a time, multiple times per year. At different stages of the project, excavation units and sample locations may be opened or revisited multiple times, with some extended over different periods of fieldwork, and new units opened adjacent to old ones. And over time, many different researchers are involved in data acquisition and recording. Total stations and other equipment are set up and packed down each day and may be operated by different people with different skill levels. For instance, students on a field school will use the total stations to learn, and many may not have used one before. So take all of this and throw in a highly active and dynamic contemporary environment subject to erosion and the effects of farm activity, and you're presented with multiple challenges in ensuring that geospatial data are accurate and comparable both within and across field seasons. So here we present examples of 2 such challenges, as well as the solutions adopted and lessons learned. Those challenges are: 1, attaining consistency in recording geospatial data with total stations, particularly limiting the error associated with spatial drift within and across field seasons. And 2, maintaining data integrity, which is capturing data entry errors and ensuring consistent recording of metadata, both of which are important considerations when publishing open data. But first, to error in spatial measurements. So drift in measurements across the X, Y, and Z coordinates is inevitable. An example of drift is on the slides on the left-hand side there, where you can see an offset between 2 deposit surfaces, the purple and the green, which in reality should actually line up. Now, of course, total station machines and the target prisms have their own inbuilt error, but drift is also compounded by the added factors of using different machines with different operators, slight variations in day-to-day setup, even when using the same station points, as well as changes in environmental conditions. So differing degrees of error in spatial measurements might be acceptable depending on the context of the project. For example, when surveying transects over tens to hundreds of meters, a small amount of error is probably negligible. However, in other cases like cave deposits, which might be spatially constrained but have quite thick and reflect deep time, this error might be more of an issue. In such contexts, the z-axis or elevation in particular becomes very important as a proxy for time and formational history. In our case on Ahuahu, we require high precision and accuracy because we're interested in the spatial distribution of artifacts between small and large excavation units. We're also very interested in the formational histories of the deposits in which the artifacts lie, and often employ finer recording methods to measure things like dip and strike to record information about the orientation of artifacts. So one way that we identify and deal with drift is by aligning our excavation units to a 1 by 1 meter grid where possible. This helps to control drift on the X and Y axes, since, for example, we can map a unit on the GIS that's located 20 centimeters from an existing one, and that might translate across to the real world initially, but on subsequent days, measurements might be slightly off. We'll be able to see that drift relative to that grid. Another solution was establishing several permanent station points, permanent in inverted commas, across the island near major areas of interest. If at the start of a new season, new station points need to be shot in, these are recorded using those permanent station points in the initial setup. So the use of these known points first and foremost each season is another way of usefully reducing error between field seasons, but also for checking and aligning spatial data from different sources, such as total stations and GPSs. Now back to permanent. Permanent station point in the context of a working farm and dynamic coastal environment is, or there's a term that takes on different meaning. So to this end, for redundancy, we established many more station points than we probably needed. Now we also account for drift in the Z-axis or elevation by recording the same 4 control points with the total station every day. Then subsequent days' measurements are aligned to the first day using these control points. And in this way, all spatial data are recorded by each total station are internally consistent. Importantly, any changes or corrections made to measurements or coordinates are recorded in the associated metadata for each record. And that is a point to which we now turn. So maintaining data integrity and consistency is important for ensuring data are comparable within and across field seasons, but it's also essential when publishing open, reusable data. Open, clean data are key to validating and reproducing research, but are unproductive if inherent errors are not made known. So when we refer to clean data, we mean data that are organized consistently, where issues are identified and rectified where possible, but importantly, they're properly documented with metadata. That is, a record is made of how data were generated, their original state, and what changes were made and why. Producing clean data is no trivial task, and in many cases, large amounts of time and effort are required to properly prepare and curate data, particularly if this process is undertaken back in the office or the lab, well after fieldwork has been completed. So one way that we ensure data consistency and comparability is by using a common database schema. And in fact, this schema is used in a range of our projects, not just Ahuahu. In the schema, the minimum recorded unit is an object, something that can be picked up, or a feature, something that is immovable. Each object and feature occurs in an area of interest, typically, or AOI, typically an excavation unit, which in turn is associated with a wider place of interest or POI. For Ahuahu, you can think of these as sections of the island. All objects and features are assigned unique ID numbers, and each record in the project's relational database includes all of the base locational variables that I just described. Now, this recording schema applies not only to spatial data, but also to things like photographs and scans of section drawings. Each of these are also assigned a unique ID number and have the same locational variables recorded as excavation units and artifacts. Importantly, each record in the database has a source ID number. A source ID is a record, each with its own unique ID number, that exists in a related table, which contains information about the equipment used for recording, the date of recording, and any associated points. For instance, with the total station, those points might be the foresight and the backsite for that day. Now, despite the common database structure, with thousands of records, human error inevitably creeps in and often results in issues such as duplicate ID numbers. To this end, records are scanned every day for duplicates and rectified at the point of detection in both the relevant database tables and on the GIS. And an example of a simple protocol we employ to minimize this kind of issue is by entering ID numbers twice when registering a find or some record into the project database. This is something that takes very little time to do, but dramatically reduces the time spent identifying and correcting duplicates after the fact. Now, metadata, of which source IDs form a part, are recorded as thoroughly as possible. So as I said, metadata are records that are kind of in the background that tell us exactly how and when a given observation was recorded and with what equipment, as well as what changes that record has undergone, if any. Part of this involves maintaining instances or copies of data in all states, for example, pre and post fixing, and strict version control is used there. Ultimately, metadata allow us to identify, track, and rectify any future errors and help us to understand the context in which data were recorded. And this is useful for if and when we, or indeed researchers from outside the project, need to revisit those data. Metadata also play a role in providing transparent documentation of data sets, and this is of increasing importance as the call for openly available data sets and reproducible results grows within the discipline. So as discussed, there are many different factors that contribute to error in geospatial data, such that it can be mitigated, but not necessarily prevented. And this is okay. The important thing is that errors are identified and addressed to the best extent possible and are properly documented. One of the best protocols is the simple age-old method of constantly and consistently checking, and checking again. To this extent, all of our data management, from initial acquisition through to the final incorporation into the project database, follows a procedural workflow. And following this consistent set workflow helps us to identify and mitigate error that creeps in at different stages due to things like many different researchers contributing to the data recording, as well as a bunch of other issues that I talked about. The use of a common workflow, as well as a common recording schema, also means that activities like excavation, with its fine-scale recording of deposits and artifacts, or wider landscape survey, where features are recorded across larger spatial scales, or something as simple as photography. All of these activities have similar built-in controls for identifying and fixing error, which ultimately makes those data sets relatable. Furthermore, with regards to data management and cleaning, the set schema with source IDs is key to what we might call preemptive cleaning, by creating the ability to identify, track, and rectify errors, as I just mentioned. And arguably, ensuring that this protocol is followed is of greater significance than increasing the speed of data collection. Machines are used for recording data, but it's humans that are required to operate those machines and human involvement that is needed to determine relationships between data points and interpret them. So we need to think carefully about the time spent dealing with data integrity. To finish, it is worth noting that none of the issues that I've outlined in this talk are new, but it is useful to be reminded that these issues do exist despite efforts to curb them. These issues are particularly pertinent to us on the Ahuahu project, but we would argue also to other large-scale multi-season projects as well. Of course, the extent to which these issues are a concern may vary from project to project, but should nonetheless be dealt with, or at the very least, processes should be documented as best as possible so that the data are easily understood and usable by researchers in the future. Failing to take into consideration sources of error in geospatial data may result in those data painting a different picture to that of their physical counterparts. And this should be ideally avoided, since after all, we can rarely go back to re-record our excavated material in its original state. So that's everything. Thank you very much for listening, and kia pai tō rā.